and I'm going to be talking to you about a new project that we have launched as an open source project as of this meeting. So this will be the first meeting in which we talk about the unrolling of this new capability over the coming year. I'm going to start off by talking a little bit about the team. I want to tell you about what Pamela is. Pamela is the name of the project, but it consists of many pieces, not all of which are available today, but some of which are. I want to give a history of the origins of the capability, an outline of what the pieces are, very briefly. I want to try and give you an idea of what we mean by model-based programming, what this modeling language is, to see so that you're able to judge whether it might be useful for things that you're doing or for people that you know might be useful with it, it might be useful for. I'm going to talk a bit about backends. Backends are things that plug in that the language can compile down to. And we're going to talk quite a lot about visualization because a large part of what we have open sourced as of today includes the visualization piece, largely due to Tom Marble, who will give a demonstration of how that fits in with the overall story that I'm going to outline. So really my job here today is to try and tell you what it is that we're bringing to the table. And we also have an unsession this evening, so whereas I'm going to give an overview if you want to drill down and ask detailed questions or have an online session in which we look at the internals a little, that would be for this evening. So we hope you come. Okay, I work for a small research company in Massachusetts. We do government-funded work, mostly funded by DARPA. On this particular project, as myself, Andreas Hoffman, who worked with similar technology on his PhD thesis at MIT, Prakash Mangwani and Dan Sears, who are both in the audience somewhere. And Tom is a consultant for our company, is playing a major role in the construction of this capability. And of course, we're open sourcing the project with the intention of building a wide community, which is primarily why we're standing here, to try and attract people to contributing as well as using the capability. So we hope that some of you within the audience will become contributors over time. So what is Pamela? I've already mentioned that it's open source. I should say a little bit about that. We're funded almost entirely from government contracts, research contracts. The majority of what we do ends up as articles in journals and in conferences or final reports. There's not much that we deliver that's real. But over the last 15 to 20 years, the government has been pushing for the research performers to produce their results in the form of open source software. Largely, this means that people either say, no, we're not going to do it, or they say, okay, we will, and at the end of the project, they begrudgingly put something up somewhere, and you usually need a password to get at it, and is essentially useless. We actually wrote into our proposal for the base Pamela project that we were going to make this not only open source, but attempt to build a vibrant community using it. And I'll tell you why in a minute. So what is the philosophy of this language? The idea is that we build a lot of complex algorithms, AI algorithms I'm talking about particularly, constraint solvers, planners, learning algorithms, and they require a lot of expertise to use well. And it's not so easy. It's easy to build a little learning example that does learning over a fixed data set. But if you want to build a complex application in which learning is just part of it and another part of it might be constraint solving, what tools do we have for building systems like that? And we're hoping that this is an answer to that. So the essence of the idea is we want a modeling language that makes it easy to express problems which involve complex algorithms to produce them. And hopefully this will lead to the ability to build more interesting applications, especially in things like robotics, because a large part of a modeling language is that we are modeling other systems. It's not just a piece of software. Finally, PDDL, for those of you who intersect with the planning community will know that PDDL is the language default for defining planning problems. It's grown rather old, and it has some baked-in constraints. There are now a large number of different splinter versions of PDDL, but they're all constrained by some of the constraints in the original version of PDDL that are hard to get away from. We are proposing to replace that wholesale while supporting all the capabilities of PDDL in its various incantations like 3.0, while removing the limitations that get in the way of many of the things that we want to do in our research, and hopefully others in the planning community will too. So those things we'll talk about in future conferences, but this is the philosophy and the drive that we have for getting this out into the community to help our research community, but also people building complex applications.
Excuse me, we're going to lose slides for just 1 second.
I've got the blue screen of death.
Well, you can describe this spacecraft and
Yes.
get people excited about it.
Picture, if you will. There we go.
Yes.
Yeah, that's right. So it's important to talk. This Pamela project is building on 20 years of research and development. It spans back over a lot of languages. I've got a short list of language antecedents there. In the documentation we have more. This isn't an idea that we just baked up last week. This is an attempt to finally get out into the world something that has been around for a long time, but has only existed in individual research institutions. Examples are Xerox PARC, NASA, and MIT. Brian Williams, with whom I worked at MIT, and my colleague Andreas Hoffman also worked, has an implementation of RMPL that, in fact, I implemented while I was there. But no one can use it because it's not open source and not willing to give it out, constantly under change. The same is essentially true for many of these languages, and that's the problem. The problem is that people who want to do this are left with having to start from scratch, and it's a lot of work. So finally, we're going to have something that captures the elements of all the things that can be done in these languages in a way that is ideal, especially for closure. Dating back as far as 2001, in the Deep Space One mission on an autonomous system, the spacecraft depicted in the picture there ran autonomously for a period of time as an experiment in which it was able to reason about the state of the spaceship and correct failures that were induced deliberately by NASA to test the capability. So that's an indication of how far back this technology goes. At the bottom are the thanks to DARPA for funding two of the contracts that are providing for the development of this. Okay, so one of the ideas that we have here is that if we want to have a vibrant community of models and a vibrant community building upon the capabilities provided by Pamela, we want some way of exchanging useful models. I'll give you an idea in a moment by what I mean by a model, but I mean a model for things like a cell phone or like a robot that has so many degrees of freedom. We shouldn't have to start from scratch every time. In the 3D printing world, we have things like Thingiverse, where we can go online and we can find examples of models that are close to what we want, which we can then manipulate into what we really want. If we can do that with models of cyber-physical systems, simple ones like robots and phones or little thermostats, whatever, we can start from other people's debugged capabilities and subclass them and create better versions. So for that, we will be providing a database, an online database capability based on the idea of Thingiverse and providing an open source free platform for other people's models. In the back-end arena, the modeling language interfaces essentially with back-ends. When I spoke about having complex solvers that we would compile down to, those are the back-ends. We will be providing some of those backends ourselves. We'll be providing interfaces to existing backends, especially the free ones, but also to some of the ones that are not free but people really want to use, like CPlex and MATLAB, that some people absolutely require. We can provide interfaces to those. Visualization is very big. Debugging these systems isn't easy, and we want to be able to see what's going on and see what the system thinks is going on, which is why we will spend the better part of this talk talking about visualization. So, what is a model-based program? We're talking about cyber-physical systems. It's not a program that runs all by itself on a computer somewhere. We're talking about modeling something that exists on the other side of a dividing line. So this dividing red line here divides the plant, which is the cyber-physical system. It may be a totally software system, like a speech recognition system, but it may be a robot that has some software running on it already, and we can interface with it, we can monitor its behavior. And our models live up here. We can divide the model essentially into two parts. The model that describes what goes on beneath the red line, what the capabilities are, what commands can we send to it, what observations can we get from it. And then a control program in which commands are pushed down to the platform in response to what the program tells us to do. So it's like a conventional program, except it's not running on a computer. It's pushing commands down to a cyber-physical system of some kind. And the various components in the architecture involve interpreting the observations, which largely means understanding the state of the system based on what we observe, and building a plan for how to get what the program is asking us to do, which is described in a high level, achieving a state, by a sequence of commands given while tracking the state that the system believes that it's in. So these are the broad category of pieces in the system. So given that, let's take a very simple example. And I'm not going to talk about the language syntax, but I am going to give some example that has a large number of parentheses in it so that everyone's happy. In this example, picture, if you will, a battery right there, and a switch there, and a light bulb. Here we have a simple circuit that when the switch is closed, the light goes on. We could imagine that there is a sensor that can detect whether or not the light is on. It's not part of the circuit, but it's part of the interface with the model. And we could also imagine that we could have a control for this switch. That switch could be a physical switch that the human throws, or it could also be controllable by sending a command that says on or off, which flips the switch. So if we want to model that, we can divide it up into components. Most interesting systems are made of collections of components. Here we have a system in which on the left, I've arbitrarily divided it into the battery and the switch. So there we have a single component, which is the battery and the switch. And that's, we could have had the battery and the switch as separate components. How we divide it up is arbitrary. And over here, we have the light bulb. There you go. There's the light bulb. And so we have essentially this component with two terminals, this component with two terminals, and some connections that wire them together. That's what we need in our model. So let's see how we do it. I'm going to go through this quickly. Don't worry about the syntax, and I'm not going to explain everything. All we need to know about this is that we're defining values, what are going to be used for the power values, high and none. The power can be high or it can be non-existent depending on the switch. And we can define a class for the powered switch. And now I'm going to add piece by piece to that definition. So first of all, we can have fields. You can think of it like a data structure. What we want for the powered switch is a terminal pin for the ground and a terminal pin for the power. And we need some value that represents the state that this object is in. It's going to be a power value. It's initially going to be none, so that when this model starts up, it will believe that the power is off, regardless of anything else. If we start getting observations to the contrary, that will change, but it will have an initial value of none. So now we can define modes. A mode says what state something can be in. And when something is in a mode, there are certain things that are true. We can specify modes. In this case, we have three obvious modes. The mode that the switch is on, which would have the condition that the power is high. If it's off, then the power would be none. And there's also the failed state, which doesn't have any condition at all, because you can be in a failed state without having any conditions on it. It can just break. So at any point, it could be broken, and it could be showing signs of being on. It's ambiguous. If the power switch is on and the light is on, it looks like it's okay. But if we turn the power off and the light stays on, then it was actually broken all along. So these can be in conflict, and it's for the reasoning algorithms to decide what state it believes it in. For that, we have a belief state. If we have a state, we can transition between them. Here we have transitions, non-deterministic transitions that can happen for no particular reason. These are just the names of the transitions, but this says we can go from the off state to the on state. We can go from the on state to the off state, and we can go from any state into the failed state, and we can even specify the probability that will happen based on statistics of how often these things fail. How would it transition from off to on? If it was a switch that was human operated, that just means a human changed it. The system knows that it's possible to go from off to on without being commanded, and if we have observations, then the reasoning system will update its belief state to believe that the human turned it on. Sometimes, however, we want to control it and explicitly tell it to go on by sending it an on command. So we can have a method. This turn on method doesn't have a body. It's a primitive method. It's one of the ones that you can push down. And this says that if we are in the off mode to begin with, we will end up in the on mode, and it will take between 1 and 3 time units to get there. It's useful to know how long it will take. Sometimes when you switch something on, it's not instantaneous. And the reasoning system that wants to reason about what's going on needs to know if after 5 seconds we've switched it on and it hasn't happened, that probably means it's broken. But if after 2 seconds it hasn't come on yet, then we can wait a bit longer. We shouldn't jump the gun and assume that it's not working. So time bounds enable the reasoning algorithms to better reason about state transitions. And I've only put one of the methods here because the other ones are obvious. So what we have here is a model that essentially gives us this. We have our 3 modes. We have transitions between on and off that can happen without being commanded, such as by an external event like the human turning it on. We have methods that can explicitly turn it on and off, and the planner can schedule those commands to be called in order to achieve an intended state. And we have failure possibilities, and very often we have a reset function so that we can try to get out of a fail state by doing a reset. And we can have probabilities on how likely it is that that reset is going to work. Okay, for the light bulb, very much the same thing. We have bright and dark as light. We expect that we'll have observations from a sensor that will give us evidence in support of the light being on or not. And we have fields both for the estimation of the illumination and the sense input. I think we've covered the essential elements of that. Finally, there's the wiring up of the model. Here we have a circuit. We instantiate a light bulb. We instantiate a powered switch. And the source and drain variables here are the same. We use logic variables very much in the same form as with Prolog to do the wiring up. So we can have an arbitrary number of components that are wired up automatically using these logic variables. Once we have a circuit in place, then the entire model that we've created gets compiled down to a data structure representation, and the back-end solvers can reason about state based on observations. It can run a program that wants to achieve a desired state by planning out a sequence of commands that it pushes down, and all it needs to know is the model that we've provided. And that can be for a cell phone, that you can send it a command to start recording voice or stop recording voice. Generally, the cyber systems that we're dealing with are complex systems that are doing a lot of things by themselves, and we have a rather crude level of control of them, like turning things on or off, sensing things at a rather crude level, like is the light on or not, enough to be useful. But the cyber physical systems generally have their own life and an enormous amount of complexity that we don't represent every piece of in the program. So I've spoken about wanting to achieve a desired state. So how do we do that? So these are done using control programs. Control programs have a lot of capability to measure things like the values of states. We have state variables. It's beyond the scope of this talk to go into what we can do with state variables. But if we run something that establishes some values, we can do something or not do something based on whether those values are a certain value, or as long as they are, or until they become, and so on. I should mention that there are various back-end representations of these, some of which you're going to see in a moment. One of them is the temporal plan network that allows a temporal planner to reason about the timing constraints and the dispatching of commands that are pushed down to achieve this. So let's take a quick look. We have one of the projects involves a quadcopter. Here we have a simple program that you're going to see running in a moment in the demonstration, so it's worth talking through. The idea is that the quadcopter is going to fly around a car. It's going to find flat tires, and then it will talk the user through changing the tire. Someone who doesn't know how to change tires, the quadcopter will have a repair manual in the model and will give verbal guidance to the user on which lug nuts to remove and so on. It's a sort of a simple example of a robot-assisted repair manual. And so here, the plant goes to a particular waypoint. This is a 4-waypoint example. It goes to waypoint A. It takes a high-resolution image. It processes the image and moves on to B. It processes the next image that was taken from B and moves on to C. It processes the previous image, C, and moves on to D. And then it finally processes the last image. And as you would expect, we have other methods to implement those. So for processing, we extract evidence from the image. And then based on what we've found, and this is where the state constraints come in, but I don't have them in this example so as to keep it simple. In parallel, we choose one of the 3 interpretation algorithms based on the evidence. and finally, to process and move on in parallel, we go to a waypoint and we do the plant process, which is all of this. So we can build complex models, complex control programs, and depend upon planning technology to make sure that they get sequenced correctly, and state estimation to make sure that the states that we depend on are actually achieved when we run them. So at this point, I'm going to hand over to Tom. And
Great. So now's the time that we get to do live demos, which are awesome. I'm really excited about the chance to do this. So thank you, Paul. Paul was showing you the Temporal Planning Network, or TPN, implementing the quadcopter mission. And so in addition to the PAML language, one of the things that we've been working on most recently is PlanViz, which is a planning network visualization tool. And let me start by just saying briefly that we have, as Paul mentioned, pushed all this code up to GitHub under the DAL Labs organization. You all probably know how this works. I just want to highlight a couple of things about the open source process. The code that we've published is under the Apache 2 license, and it's using the very simple inbound equals outbound licensing model, which means there is no contribution licensing agreement that's required. We're hoping to get the community involved in developing all the pieces of this puzzle and have high ambitions for it becoming not only used for research, but also in the entire planning community in general. So with that, let me move on to actually showing you PlanViz. So this is our visualization tool, which is in a web browser, and it's actually developed using ClojureScript, and I've used Om.Next as the visualization framework. I think that I want to just make a brief digression that there are a lot of different bindings to React, Facebook React, within Clojure, and I think that for me, Om.Next is that, but most importantly, I think Om.Next brings us a very powerful data model, a very idiomatic Clojure data model that gives us the ability to do things like, I'll just say referential integrity, and it's extremely powerful in its expressiveness. In addition, what I've tried to do here with PlanViz is use the tools in the browser to do visualizations, specifically SVG drawings. Browsers now are smart enough to render SVG natively, and I wanted to actually take advantage of that in the work that we're doing here. So what I want to do is I want to show you, this is a TPN, Temporal Planning Network, that represents the bit that Paul was talking about earlier. In this, you see that this plan proceeds from left to right, and we have these state nodes where we're in between which there are activities that are time-bound, and then when you see a node like this with parallel bars, that means that both of these threads, if you will, are proceeding in parallel. So after we capture the images from waypoint A, in parallel, the quadcopter is going to go to waypoint B, and we're going to analyze the evidence from waypoint A, and then based on that, we'll choose, and that's what the circle node means, we'll choose which of the activities to take next in terms of how to interpret that data. Once we've done that for waypoint A, we're going to move on and process waypoint B as the quadcopter moves along to waypoint C, and we'll do that again. We will analyze the data from C as we move to D, and after we've done that, we'll simply analyze the data from D. Now, did I mention that this is an SVG? And did I say how excited I am it's an SVG? That means you can zoom in. It means you can zoom in all day long. It means if you really want to zoom in, you can get in really close and you can zoom in, and I just love that about SVG. The other thing is, did I mention that it's just standard web technology? This is all standard SVG and CSS. So when I come and I mouse over a node, this tooltip doesn't even close your script. I get that for free with CSS. If I come over to an activity and I mouse over it, I get a tooltip for free, and that's just CSS. There's nothing complicated going on. If I want to, let's say I want to come out and I want to select an activity, I can click on a node and I can get nice yellow highlighter around it. It's so exciting. It's interactive, and it's SVG, and it's Om.next, and it's fun tools that I get to play with. So this is kind of the technology stack of PlanViz. Now, let me show you another kind of a planning network. It's basically a different view into the same plan. This is, instead of moving from left to right in time, what I'm showing you here is a hierarchical task network, or an HTN. So what's an HTN? An HTN is basically a modular decomposition of our plan. So we start off at the very root node, which is we have a mission, and then we have major subparts, which is we're going to go to waypoint A, then we're going to interpret the data from A and go to B, interpret the data from B, go to C, interpret the data from C, go to D, and then finally interpret the data from D. Do you see I'm panning and zooming around here? This is so much fun. And then we have the details. So at every point with the plan, it gets more detailed. So for example, after we have the evidence from waypoint A, in parallel, we're going to, in parallel here, we're going to start moving to B, but once we have the evidence, we're going to choose one of these three nodes for this next step, one of these algorithms for interpreting it. Now this is important because I'm going to show you in the live demo both the temporal view, the TPN view of the plan as it proceeds left to right, but I'll also show you this HTN, or hierarchical view, of how things are moving forward. So with that, let me just show you this other screen where I'm going to start to set this up a little bit. First of all, one of the things that we did is we wanted to make a sort of a friendly command line interface for people that might be familiar with IRC commands. So that's the way that, that this works. I can simply type in a command and find out things that are going on. I can interact with the system. I can call this top window the top window. I can call the bottom one the bottom one. I can do things like a private message. I can say, are you ready? And I can say yes as a broadcast message, sort of like IRC. So wait a minute, how's that? Wait a minute, what just happened there? There are two different browsers, two different clients. So yes, it's a traditional chat application. The difference is that they're not just connected in the PlanViz server, but that PlanViz server is sitting on a RabbitMQ network. And the reason that we did that is when we have mission execution engines and dispatchers and quadcopter interfaces, we want them all to participate on the RabbitMQ network, and PlanViz is going to visualize that. And we actually have a demo of what that's going to look like. Before I get into that, let me just quick show you the view of having, now I'm showing the TPN on the top and bottom, and the reason I wanted to do this is I want to show you this thing that we've got, which is our automatic mode, or collaborative mode. The idea is, you know about pair programming, you have people that are looking at the same thing, maybe they're working remotely. Wouldn't it be nice if you could do that for visual things? So if I'm just trust me, I'm clicking in the top window. I'm going to pan and zoom in the top window, and look what happens in the bottom window. The remote user is seeing exactly what I see, and it's tracking exactly what I'm doing. So that is fun. I can also come in, and I showed you highlighting before, but let me show you this. Now if I have the hierarchical view down below and the temporal view, let's say I want to see what this first block looks like. I'm going to click on it here in the HTN view, and look in the TPN view, it's highlighted. I get yellow highlighter that shows me what does this block mean when it's actually expanded into the temporal plan? And going vice versa, I could click on one of these activities. I could say, well, which one is this one interpretation thing? And it highlights it for me in the HTN, so I can see the correspondence between those two. So that's part of our multi-user experience, where we can have multiple people collaborating on these plans and viewing different parts of them. Just briefly, I want to show you an actual quadcopter video, and I'm going to have Paul walk us through this. It's very short. Tell us what's happening, Paul.
So you can see the quadcopter up in the top left. It's flying between the waypoints that I described in the program before. What's happening is it's trying to reason about what's in the image to use the best algorithms for interpreting it to deal with difficult environments. It's taking images, it's thinking about what algorithms would work best given what it's got, and it's moving on to the next waypoint and doing more reasoning. You can see matches that it's making down in the bottom right, and this is video captured from a live run. Eventually, we'll have a much longer version that involves the changing of the tire, but for the moment, that's it. Now we can see a simulation of the same thing running on the system.
So I'm going to leave the quadcopter video running here in the lower right, and I'm actually going to run a simulated mission, dispatching it over the RabbitMQ network, and PlanViz is going to show us this plan as it executes, both in the HTN and the TPN. Of course, this is going to work the first time.
I should point out that the video is not in any way synchronized with the run. It's just there.
But you can imagine it's synchronized.
Keep you amused. Yeah.
So what's happening here is you see the nodes in the TPN are highlighting as we move from left to right. And I can actually, oops, I didn't want to do that. Something had to happen. It's a demo. So I wanted to zoom in here. As this is, you can see the colors changing. What I'm doing is I'm taking the state that's coming over RabbitMQ and I'm mutating that within PlanViz and using just CSS to color these things. Nothing could be easier, and it's so much fun. What's happening in the HTN is when nodes start, they turn blue, and as soon as they're completed, they turn green, and when all the children are green, then finally the node above it turns green, and then when we get to the end of the plan, that means the last thing is done, the root node will turn green. Yay. And so now our plan is complete, and we've done the plan, and we've understood it from top to bottom, left to right. And with that, let me end by saying we probably don't have any extra time for Q&A, maybe just a brief one, but I wanted to call your attention to the fact that we have an unsession tonight at 8:30 next door in ABC, and we'd love to go into more detail and show off, development environment, having a connected browser REPL and a server REPL at the same time. How much fun is that? So with that, are there any quick questions? Okay, well, great. Thank you so much, and hope to see you tonight at our unsession.